R-CADT is pleased to invite you to participate in the course. Regional Planning, Economy, Logistics, Infrastructure, Health, and Land Use. Sustainable development is our common future. The notion of the commitment that each generation has to its successors is at the heart of the concept of sustainable development, which was incorporated by the World Commission on Environment and Development, WECD, Brundtland Commission, 1987, in its report, Our Common Future. Sustainable development meets the needs of the present generation, without compromising the ability of future generations to meet their own needs. This can only be achieved with the rational and scientific use of natural resources, renewable and non-renewable, whose optimal and effective management is the responsibility of the rulers and all their advisors. Operations Research Applied Regional Planning. Aimed at professionals, engineers, mathematicians, physicists, consultants, economists, data scientists, software developers, etc., who require and or wish to know mathematical modeling, advanced analytics algorithms, related, among others, to the implications of Industry 4.0 and its relationship with the process of evaluating the technical economic impact of the decisions that are made. This continuing education program strengthens the analytical skills and professional criteria of the participants, so that they can exercise, share and or supervise, with propriety, the professional functions in accordance with the state-of-the-art of the methodologies and technologies that support the digital transformation of the companies. It is an important course for public servants. Mathematical methodologies. Mathematical methodologies correspond to the scientific foundations for implementing mathematical optimization models. Specific objectives. Training in fundamental methodologies to support modern mathematical modeling. To train so that the mathematical modeling of industrial and business processes is a generator of real socioeconomic wealth frequently used in our society. Understand that optimizing the use of resources is the scientific basis of sustainable development. Learn about systems and industrial market modeling. Learn the fundamentals of modeling real problems based on the integration between mathematical models and data models. Information technologies. Computer technologies correspond to the computer tools available, freely or commercially, to design and implement solutions to problems in social or industrial organizations. Specific objectives. Learn how to implement solutions applied in the real world by making use of the modern computer technologies available for the algebraic modeling of industrial and business systems. Present and manage live tools used by large companies to solve their optimization problems. Understand the state-of-the-art of optimization and its relationship to smart computing. Know the available technologies, as the principle of basic knowledge to be able to solve, in reasonable times, problems with millions of variable. Know the fundamentals that must be had for the assembly of models using the most effective technologies. Value chain optimization or enterprise-wide optimization. Operations research uses the scientific method to address organizational problems, focusing on providing management with a mathematical basis for decision-making. It is not a science, but more the application of science, logic, mathematics, statistics, and various theories to managerial and administrative problems. It focuses on organized systems, using interdisciplinary teams of scientists and engineers. Operational research began in 1937 in Britain and developed in countries such as Australia, Canada, France, and the United States. I invite you to watch the video. Applied Operations Research and Industrial Engineering and learn more about AWO. A company's value chain is made up of two chains, strongly interrelated. Demand chain determines all the processes that are carried out to attract customers in the markets, and supply chain determines all the processes that are carried out to produce the products that customers want to consume. This is also true for social service supply chains. The diagram presents the chain of the company's production chains that together make up the value chain. One of the greatest evolutions in the modeling of companies occurs in the interpretation of their value chain. It can almost certainly be said that traditional regional planning lacks formal mathematical models and it is based on mental models. While modern planning is based on mathematical models, all related to each other, thanks to computational power. The social cost of this situation is impressively costly. This evolution has led to modeling based on artificial hypothalamus, supported by the integration of mathematical programming and artificial intelligence. The power of today's technology is not in the mathematical calculations it allows to be performed, it is in the mathematical calculations we can imagine we can perform. The core model of regional planning is presented in the book Designing and Optimizing Networks for Smart Cities and corresponds to Chapter 1. A mathematical programming model for regional planning that incorporates economics, logistics, infrastructure, and land use. The book Regional Planning, Cities and Regions, Smart, Autonomous, Analytical, Integrated and Sustainable, is the course guide. The artificial brain is the evolution of decision support systems under Industry 4.0. It is conceptualized as a set of mathematical models, which exchange information autonomously with each other, working online using distributed optimization. The diagram presents some of the models that make up the artificial hypothalamus of a regional planning system. In the case of regional planning, an example of the physical systems associated with autonomous, real-time optimization models that communicate with each other are inhabitants, installations or equipment, energy, land use, companies and industries, and transport and logistics. Integrated planning of the region. Regional modeling is a planning tool based on a system of mathematical models of different types of optimization, econometrics, computable equilibrium, etc., integrated to determine the business structure and the development of the population that would exist if certain socio-economic development objectives were met. The hierarchical system for decision-making is the first step in the definition of an artificial hypothalamus of regional planning. Its structuring must consider two aspects. Time, related to the transcendence of decisions. 3 levels of planning are typically used: strategic, tactical, and operational, or in other words, long-term, medium-term, and short-term planning. Space, related to the coverage of decisions in space. This structure does not have a defined axis and therefore depends on a specific reference framework for each region. It is closely linked to the planning instruments defined in the Land Use Plan. The models included in the system are: Urban Land Use Planning, RPOURB, determines the spatial relationship between inhabitants, companies, social facilities and transport systems, using a scientific approach that projects what is the most likely future development of urban regions. Region-wide Land Use Planning, integrates the RPOURB model with FOSSUM, Forest and Agriculture Sector Optimization Model, into a dynamic nonlinear programming model for integrated planning of urban and rural regions. Regional Computable Economic Equilibrium, models urban and/or rural regional economies based on computable general equilibrium concepts through the simulation of input-output techno-economic systems. The master plans for the development of social infrastructure are aimed at determining the way in which the supply should be organized, to meet the demand in the different facilities, for example, schools, hospitals, health centers, marketplaces, entertainment centers, etc. Demand is associated with the population, which is usually dispersed in space according to the places where they live, work or simply are. For the purposes of its spatial location, demand is associated with a space, area, in which the demanding population is located. This space must be associated with a point position in the geography that normally coincides with the centroid, or center of gravity, of that space. The centroid can be calculated by considering the spatial distribution of the population in the area, as desirable, or simply by considering the shape of the space. Supply is associated with small spaces, not comparable in size to spaces where demand spreads. The supply points are associated with a point in space, so the problem boils down to establishing a connectivity tree between the service supply points and the centroids of the demand areas. Allocation of demand to supply. The assignment of demand to the site where the requested services will be served corresponds to a difficult problem to solve, since there is no universally valid theory to solve the problem. We can assume two types of allocations: those that are fully regulated by the state, in totalitarian countries or regions, and allocations based on the free choice of users. In the first case, modeling is simple and should be based on knowledge of the allocation rules. In the second case, there are at least two ways to simulate the human choice of which facility should be used to meet demand. Simplistically, let's consider that the only decision factor is distance. The traditional solution, which can be called deterministic utility theory, DTU, which assumes that the user selects the nearest installation regardless of the distance to other installations of the same type. The second methodology is based on the Rodom utility theory, RTU, established by the Nobel Prize in Economics McFadden, whose early work focuses on the application of RTU in transport choice models, Domenčík and McFadden, 1975. In this case, there is an inverse proportionality between the demand allocations to the facilities, with the distance between users and facilities. This model has been applied in the areas of economics, finance, logistics, development and land use planning. Mathematical models available for the following master plans: high-impact facilities, ports, airports, etc., academic facilities, schools, universities, health facilities, hospitals, emergency centers, etc., solid waste treatment, public space, shopping and social centers, special facilities, social development centers, libraries, etc. Food supply chain master plan. Regional food supply planning is based on mathematical models, which simulate the food supply chain to regions and cities, based on the optimization, design and operation of the logistics chain that is required for this purpose. Regional food supply planning is based on models that simulate the food supply chain to cities based on the optimization, design and operation, of the logistics chain that is required for this purpose. The aim of the model is to ensure the principle of food safety by guarantee the availability and quality of food, reduce bid prices, facilitate access for all citizens to more adequate food, and build a supply system that revolves around a food basket that in nutritional terms allows an adequate diet for the population. The logistics chain includes food collection at sources, producing municipalities and farms, transportation of food to the distribution center, and cross-docking food to other distribution centers, and food production companies in the region and in other regions. Master plan for food supply in public institutions. Optimization models aimed at meeting the food supply commitments that government entities have in different public institutions, such as colleges, dining rooms, hospitals, and disaster response. Public health systems optimization. Mathematical algorithms for epidemic management, based on highly complex mathematical methodologies, will prevent most deaths. Challenge: design and implement a DSS for pandemic management. Solution: design and implementation of a DSS oriented to pandemic management integrated by the following models. The epidemic simulation model simulates the spread of the epidemic because of a combination of control policies to deal with the epidemic, mitigation, confinement and vaccination, dividing the territory into regions and the population into socioeconomic segments. The epidemic management optimization model optimizes control policies, the use of health supply chain resources, vital resources for optimal expansion, and vaccination processes. Socioeconomic epidemic impact model determines the socioeconomic impact of pandemic control policies on the economy. Estimation of the epidemic state, hybrid predictive analysis model, based on the distributed Kalman filter, to track the pandemic. Mathematical models for the optimization of public health policies. Epidemic simulation model. It simulates the spread of the epidemic, due to a combination of control policies to deal with the epidemic, mitigation, confinement and vaccination. The model divides the territory into regions, the population into socioeconomic segments and the time into seasons, to have a dynamic epidemiological model that includes multi-infected states, multi-regional mobility and multi-social socioeconomic segments. Epidemic management optimization model. It optimizes control policies, the use of health supply chain, HCM, resources, and optimal expansion of vital HSC components. Epidemic socioeconomic impact. It determines the socioeconomic impact of pandemic control policies on the economy. Integrated with the optimization model, it can produce dynamic pandemic control strategies, which balance those contradictory objectives, which may arise in the epidemic management process, such as minimizing deaths and minimizing the impact of the economy on health, and epidemic status estimation model. Hybrid predictive artificial intelligence model, based on Kalman's distributed filter, to track the real state of the pandemic. The pandemic management optimization process involves research in the following areas: epidemic theory, smart sampling, and identification of epidemic model parameters and epidemic status, and mathematical models of optimization oriented to the control and management of the pandemic process. Integrated optimization of regional planning and public health planning. High health, optimization of public health policies, is integrated with high RPO, regional planning optimization. This implies that all the models of the two systems can be integrated through the database, using a common data model, and through equations that integrate a single holistic model, this following the principles of structured mathematical modeling. This integration is since the management of the public health problem corresponds to the problem of regional planning, as experienced during the COVID-19 pandemic. Water resources system optimization. It is a comprehensive water resource planning system, aimed at optimal regional planning, in all aspects related to the intensive use of water resources. The model addresses the multiple planned uses and/or for the control and management of resources. High water corresponds to a general model that includes all types of hydraulic components, reservoirs, hydroelectric power plants, pumping stations, pumping storage, rivers, overflow channels, connection points and water demand, for irrigation, aqueducts, environmental, industrial and others. Components can be freely linked to form any topology. Homeland Security Optimization. According to the U.S. Office of Homeland Security, Homeland Security is a concerted national effort to prevent terrorist attacks within the United States, reduce U.S. vulnerability to terrorism and minimize harm, and recover quickly from attacks that occur. The main national security applications based on operations research are: assignment issues, police patrolling the subway and bus systems. Other scarce resources include bomb detector canines, vehicles, and security cameras. Random inspection of luggage or people, assigns air marshals to vulnerable flights, assign patrols at ports to minimize the risk of terrorism and drug trafficking. Protect forests from wildlife extractors, and allocation of cameras to reduce the cost of security, on the metro and on public transport. Programming issues. Scheduling for the Federal Air Marshals Service, FAMS, on commercial flights, primarily in the U.S. Scheduling police patrols, drones, helicopters, and other security vehicles, and intelligent tracking of criminals. Localization problems. Location of security infrastructure, police stations, immediate care centers, fire stations, etc. Other. Evacuation plans. Passenger classification. Vehicular routes made of materials that minimize the danger to humanity. Disaster and emergency management. Challenge. Develop a DSS for disaster and emergency management. The overall objective is to minimize the potential negative economic impact and loss of human life. Solution. Design a set of mathematical models to address the problems arising from disaster management based on stochastic programming models. Benefit. Set of measures and mathematical models to prevent and/or reduce the impact of disasters. Prepares the community to respond best when disaster strikes. The following activities should be carried out before the disaster. Mitigation, a set of measures to prevent or reduce the impact of disasters. Preparedness, prepare the community to better respond when disaster strikes. The following activities should be carried out during and after the disaster. Reaction, the use of emergency resources and procedures to preserve the life, property, and environment of the community as disaster is occurring. Recovery, a set of long-term actions to stabilize the community and return to normal. You must be clear that during disaster there is only time to cry, whether you are prepared or not. Therefore, preparing for disaster is an activity that should be done before the disaster. Mitigation of disaster and/or emergency management caused by nature. The overall objective is minimize potential economic and human losses, and to continue the operation of the economic system. To this end, the historical behavior of nature is studied, trying to know probabilistically what can happen to make decisions about where, when and how to allocate resources to mitigate and/or prepare for the disaster. Wildfires are an important ecological process in forested regions around the world, which can cause significant economic damage and often create widespread health impacts and environmental pollution. A network optimization approach to plan treatments of combustible materials in wildfires that minimize the risk of fire spread, in forested landscapes below an upper limit for the total treated area. Simulation models are used to estimate the probability of fire spread between pairs of forest sites, and a critical node detection (CND) model is formulated that uses these estimated probabilities to find a pattern of combustible material reduction treatments that minimize the likely spread of fires. Mathematical modeling controls the size and spatial contiguity of combustible material treatments. Mitigation of disaster and/or emergency management caused by humans. The overall goal is to minimize potential economic and human losses, the social impact of the terrorist attack. To this end, models are proposed that study the opponent and hypothesize the decisions that can be made, using game theory models, about where, when and how to allocate defense resources. Attacker and defender models. The core of an attacker-defender model is an optimization model of an infrastructure system whose objective represents the system's value or cost to the defender, our society, while it operates. For instance, the maximum throughput of a pipeline network could measure that system's value, while power generation costs, plus economic losses resulting from unmet demand, could measure the cost of operating an electric power grid. Reaction and recovery after the disaster involves facts accomplished, actions during the disaster, reconstruction actions, optimization of educational systems. The services required are schedules of educational activities. It includes the allocation of resources, teachers, classrooms, course exam schedules, medium-term resource planning, student pickup/distribution routing, assigning students to educational institutions, location and sizing of facility capacity, and optimizing the food supply. Mathematical models can be customized for special business rules of educational institutions. Optimization of complex public projects. Planning and scheduling of large projects. Based on mathematical programming models that optimize the execution of large projects through the optimal allocation of project resources. Optimization of decisions for the selection of investment or business plans, based on a mixed binary programming model that contains the constraints associated with the logic of project selection processes, which must respect constraints of different types, which may be social, economic, technical and/or public policy. The model must be stochastic optimization, in such a way that decisions are made that contemplate probable scenarios of economic development, selecting a portfolio of business plans that, in terms of expected value and risk coverage, are the best according to the organization's decision criteria. The objective is to determine the investment plan that allows to balance multiple objectives, such as maximize incremental sales, maximize the jobs generated, maximize private investment, and reducing extreme poverty. Public project management. Computable platform to support public management for the planning department of large cities based on a computable general equilibrium (CGE) framework to simulate the evolution of the city's economy and its area of influence because of the execution of planned investment projects. Smart grids in smart cities. The high models for smart grids are made up of forecasting and optimization models, aimed at supporting decision-making for smart grid operators, optimization of the economic and technical aspects related to smart grids and electricity companies. Building and housing demand response, optimization of energy management in building complexes, such as universities, shopping centers, office buildings, homes, housing estates and/or small towns, and industrial energy efficiency, optimization of energy management in heavy industries intensive in energy consumption. High L and high SGO are integrated into high power that integrate input-output data models around a common data model, allowing models to be connected automatically through the database. The main optimization models are Smart Grid Economic Dispatch, Smart Grid Network Design, Smart Grid Unit Commitment, Smart Grid Maintenance, Smart Grid Network Reconfiguration, and ETRM Energy Trading and Risk Management. The main forecasting models are Forecast Renewable Energy Sources, and Forecast Electricity Demand. Electric Vehicle Management. It corresponds to the planning of the management of electric vehicles, which is a major problem, given the changes of all kinds that the introduction of this new technology implies. High L and high SGO are integrated into high power by means of a common input-output data model, which allows models to be connected automatically through the database. Real-time distributed traffic optimization. This is an important area of research and development for high. Optimizing the synchronization of traffic lights in a traffic system is a difficult problem, linking complex areas with complex traffic networks. Solving the integrated problem, as a monolithic problem for a large city, is impossible. The division of the problem into zones facilitates the solution of the total problem, and the connectivity, based on principles of mathematical optimization, between the different problems, zones, ensures that the system travels the path of optimality. Current systems of intensive information capture, smart metering, allow optimal operating conditions to change dynamically, as the behavior of traffic in the city changes. Challenge. Develop an artificial hypothalamus based on distributed optimization algorithms, which can handle the computational complexity of the problem, and find near-optimal solutions in real time. Distributed optimization decomposes the problem at the traffic network level, into several independent subproblems at the intersection level, and solves them in parallel. Decomposition is achieved by identifying the constraints represented by the interrelationships between subproblems and relaxing them. Distributed coordination pushes solutions towards global optimality, by exchanging information between subproblems that share a relaxed constraint, and reinforcing relaxed constraints on subproblems, by incorporating information received from other subproblems. This method is incorporated into traffic model predictive control to account for the dynamic nature of the problem and further reduce computational complexity. Design of port and railway megasystems. The growth of the port sector, driven by the growth of maritime transport, entails the execution of megaprojects aimed at the construction of sustainable port and railway systems. This is an opportunity to use operations research methodologies for regional planning, including semi-detailed port operations. These models must be integrated to quantify the impacts of port region decisions, to carry out regional planning that maximizes the well-being generated in the social surplus, and that guarantees the sustainability of development plans. R-CADT. Visualization of results. The model describes the dynamic evolution of multiple variables that serve as indicators of the development of the territory. Some variables are predominant use, area occupied by housing, public space, industry, equipment, roads, density, land available, and so on. New means of visualization, such as those offered by R-CADT, allow the results to be visualized through digital twins, which accelerates the understanding of what the territorial model analyzes. The simultaneous visualization of multiple of the variables included in the model is also obtained. The image presents the simultaneous visualization of areas of landslides, floods, earthquakes. In 2006, the OptEx, R-Sinfo interface was implemented. HI is currently working on the OptEx, R-CADT interface. The course director is the founder and scientific director of R-CADT. Engineer Velasquez Bermudez's experience in applied operations research dates back to 1972, which means that he has accumulated more than 50 years solving real-world problems, doing engineering consulting using mathematical models. This is the technology transfer that those attending the course will receive. RCADT and/or HI issues a certificate signed by the scientific coordinator, for which the student must participate in at least 20 conversation sessions. R-CADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information, you can consult the URL. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.